mean, I don't believe in that it's wrong. It's actually correct. It's absolutely right. So if you are okay about any, all the calculation I did on the board before the break, that's okay. I mean, you can just ignore, what I'm saying here. But actually, it was unnecessarily complicated. Actually, okay. So then I'm gonna give you a simpler explanation. Okay, so here, remember that what we want to do here is to check that player 1 and player 2 has no incentive to deviate, right, from the trigger strategy. So especially we want to show that player 1 and player 2 has, they are supposed to choose E all the time on the equilibrium path, and we want to show that there is no good benefit from choosing S instead. Okay, so then actually what we have to do is we only have to check for the we only have to check the player 1's incentive in period 1. Why? Because let's say that player 1 has the incentive to deviate in the first period, okay? Then they choose E and E, and in the second period, if you think about sub-game, beginning from the second period, then that is just exactly equivalent to the entire game itself, right? So we use the kind of similar argument when we talk about, infinite horizon bargaining game, and we use the same argument here again. Okay, so if you think about sub-game beginning from the second period, actually that is mathematically equivalent to the entire game, right? So if player 1 has no incentive to deviate in the first period, then player 1 also has no incentive to deviate in the second period as well. And that also means that player 1 has no incentive to deviate in the third period, etc., etc. Okay? So what we really have to do is we have to check player 1's incentive in the first period. Okay? So we actually have to check only this one. Okay, so suppose player 1 choose E all the time, then payoff is the total payoff is this one, right? And this is only equal to 1 over 2 over 1 minus delta. Okay? And if player 1 deviates in the first period, then what is payoff? Player 1 can get 3 in the first period, right? Instead of 2, he gets 3 if he deviates in the first period. But in the next period, payoff is 0, or actually 0 all the time, right? So you only have to compare this payoff and 3. Actually, that's all that you have to do actually. And this one is larger than this one if and only if what? 2 is larger than 3 minus 3 delta, right? And this is the case if and only if 3 delta is larger than 1, which is the case if delta is larger than 1/3. Okay? And that's the way I also derived this thing here, delta larger than 1/3. So delta is larger than 1/3, then this payoff is always larger than this payoff. So we have this equation. Okay? So actually this calculation is actually, if you check carefully, this thing is actually just equivalent to what I did before the break, but probably this presentation is much simpler and easier to follow. Okay? So here we use, when we did simple thing here, when here we kind of use the recursive structure of the game. Recursive means that the same structure is repeated over time, right? I mean, whatever happens beginning from first period is exactly like whatever happens beginning from second period, etc., etc. So basically, the same structure is recursively repeated over time. So we use that property here to simplify everything. Any question? Okay, so what I'd like to do next is, so far we have solely focused on the case without asymmetry information, right? I mean, our discussion on normal form game assumes that the structure of the game is common knowledge, right? And there is no really asymmetry information. Both players know everything relevant to them. Okay? And when we talk about extensive form game, we also mostly focus on the case that there is no asymmetric information. Okay? I mean, at the end of last week's lecture, I just gave you some example of extensive form game with asymmetric information, probably a couple of examples, but we really didn't discuss any details about those games, right? So most discussions so far just have focused solely on the case without asymmetric information. But if you think about what's happening in the real world, the topics that economists might be interested in, basically asymmetric informations are everywhere. If you think about bargaining, for example, probably I mentioned this thing, probably a couple of weeks ago. Here in our example of bargaining game, we assume that there is no asymmetric information, right? If you frame everything as price negotiation between a buyer and a seller, that means that a seller's preference or seller's value of the good is common knowledge. The seller knows how the buyer values my product. But if you think about real world, sometimes that's not the really case. I mean, the seller really cannot tell what is the buyer's value of my product, right? I mean, the reason is that we know that typically different people have different preferences. Okay, so my preference is probably very likely to be different from yours. Okay, so it's actually really stupid assumption if we simply assume that all players or all agents have exactly the same preferences. So which means that when you begin negotiation with your potential buyer, it is very likely that you are uncertain about your potential buyer's preference, which means that you are uncertain about his or her value of your product. Okay, and if you think about other applications, for example, if you think about the contractual relationship between employee and employer, so in this case, employer has to pay some wage, and as a return, employee has to do work, right? And employer obviously really cares about productivity of employee, right? But which kind of ability of employee. But again, ability of employee is typically uncertain. Probably I know better than, sometimes I don't really even know what is my ability. But at least what I can say is that at least I have a better idea, about my ability than my boss, my employer. So in that case, you can also say that there is a specific information between employer and employee about the ability of the worker. Okay, so in the second half of the lecture, we mostly try to extend our framework to the extent that we can, so that we can accommodate some asymmetry information into our framework. Okay, so we like to extend our framework so that we can have some component of asymmetric information in our game. Okay, but before we do that, the first thing we have to do is we have to talk about how to model uncertainty, knowledge, and information. Okay, so that's the first thing, and that's what I want to do here right now. So there are many different ways, potentially many different ways to model knowledge and uncertainty and information. But the one I'm gonna present here is probably the most popular one among economists, kind of standard. We use this kind of framework, most of us. Okay, so here, I'm gonna mostly I'm gonna use very specific example, which is easily generalized. So this is example I'm gonna stick to mostly today. So let's say there are two random variables we are interested in. So the first random thing, so there are two uncertainties we care in this example. The outcome of the election and the outcome of stock market. Okay? So this is actually, the example I used several years ago when there was presidential election in US. So actually, there are two candidates in the election, Trump and Hillary. Okay, so the outcome is just either Trump wins or Hillary wins. Okay? And there can be potentially infinite ways to describe the stock market outcome. But for now, here in this example, to simplify our discussion, I'm gonna focus on two simply, I'm gonna say that there are only two possible outcomes. Either stock market goes up or stock market goes down. Okay? So there are four possibilities then. So here, this is Greek letter omega. So in this set, I just list all possible outcomes in our context. So TU, that means Trump wins the election and stock market goes up. Okay? And TD, that means Trump wins and stock market goes down. HU, that is Hillary wins but stock market goes up. HD means Hillary wins, stock market goes down. Okay? Okay, so then you can, so we call this set omega, capital omega. We're gonna call that state space. So state space is just collection of all states. We list of all relevant states. Where state means each state specifies every relevant details of the environment we are interested in. Okay. So here, this is just one example, but you can cook up many different examples depending on content. But the thing is that omega has to include all potential states we care about. Okay. And sometimes state space can be infinite. For example, if you really care about exactly what is index of stock market, then the state space will be infinitely many states, right? From 0 to, there is no upper bound, right? Stock market index can be 0, 1, 2, 3, even some decimals. So the state space will be infinite in that case. But for now, and this today's discussion, we are going to focus on the case that state space is finite. So which means that there are only finite relevant states. So in this example, there are 4 states only. But our discussion easily can be extended to the case with infinitely many states. There is no really big difference. Okay, that's the state space just lists all potential possible states in the world. The next step is how to model, based on this state space, how to model different informations across different people. Okay, so we're gonna use this kind of trick. So we're gonna assume that a agent I does not know which is the true state. So in this example there are 4 states. So basically, if you want, you can say say nature choose one of them as the true state, right? So the nature or God tell what is the true state. But we're gonna say that agent does not know exactly which is the true state, but instead this agent, he or she knows instead only which element of a partition of state space contains the true state. Okay, so this is a little bit abstract, but it's really easy to follow it with this example. Okay, so there are two agents. Okay, so again we are talking about Hillary from the example, stock market, Hillary from the example. So there are two agents, agent 1 and agent 2, and let's say the election outcome just realized. Okay, so election outcome is just given out, but it is not really appears on the so it's not really publicly announced yet. Okay, so let's say you can think of agent 1 is kind of the guy who is the observing the entire process, right? So he's kind of the first guy who knows the outcome. Okay, so if you think about player 1, then however agent 1 he's in the observing the process of election, so which means that he does not observe exactly what happens in the stock market right now. Okay, so which means that player 1 knows either Trump or Hillary wins, but does not know whether stock market is going up or going down. Okay, on the other hand, agent 2, he or she is exactly opposite situation. So agent 2 is working for it's kind of trader or whatever it is. So he or she knows how the stock market is going on, but does not know yet what is the election outcome. So agent 2 can tell whether it is stock market is going up or going down, but does not really know whether Trump wins or Hillary wins. So in that case, you can say that player 1. So player 1's information can be modeled this way. So without this curly bracket, if you just ignore this curly bracket, so this is exactly list of 4 possible states, right? So TU, TD, HU, and HD. But I grouped the first 2 things together and last 2 things together. So which means that agent 1 can tell whether true state is here, the first group, or in the second group. But so for example, let's say the true state is Trump wins and stock market goes down. Okay? So that means the true state is here, TD. Then agent 1 can tell whether true state is here or here, which means that agent 1 can tell, okay, stock market, I don't know, which one is the correct state, true state, but I can say at least true state is in this group. Okay, so which means that, and at the same time, that is to say, he can say that true state is not in this second group. Okay, so and if you look at this partition of state space carefully, it is exactly the case that player 1 can tell the election of the outcome of the election, but cannot tell the outcome in the stock market. So in other words, player 1 cannot tell apart TU from TD, right? So TU and from TD, he does not know which one is the correct true state. He can say, and this true state is either TD or TU, but cannot really say which one is true. Okay? And on the other hand, player 2 has, so again, we have 4 all possible states here, but similarly before, player 2 can tell whether true state is here or here, but cannot say anything further. Okay? So in other words, player 2 can say whether stock market is up or down. So if true state is here, that means stock market goes up. And if true state is here, that means stock market goes down. So agent 2 can say that, tell that, the outcome of the stock market, but does not know the election outcome. So that's the way we model asymmetric information, difference of knowledge or information between agents. Okay? So mathematically, in game theory, if you say that player 1 and player 2 have different knowledge or different information, that means they have different partition of states. Okay, then we call actually each partition here, TU, TD in this the middle line, we call this is a information set. So player 1 has two information sets. So first information set consists of TU and TD, and second information set is including HU and HD. If you remember, what we discussed last week, we used the same term to describe, some uncertainty in extensive from game, right? I mean, when we talk about the case that a player cannot distinguish two different nodes, we also use the same term, right? We said that two nodes are in the same information set. So we actually use exactly the same idea here. Two states in the same information set, that means this agent cannot distinguish two states. Okay. Okay, a little bit of notation. So the small omega, so this term, this letter here, it looks like W, but actually it is Greek letter omega. So omega, small letter omega, generically means a element in the state space. So omega is a particular state. And pi omega, that is partition in player 1's information set, pi in which omega belongs. Okay? So for example, in this example, it's just a little bit of notation, kind of promise between you and me. So P1 TU is in this example. So this is the partition that of player 1 that TU belongs to. So if you look at this example, TU belongs in the first partition here, in the middle line. So in this notation, by this notation, what I mean is TU and TD. Okay? Which is also equals to TD, right? Because TU and TU, both of them are in the same. So the second breakpoint is kind of repeating myself again. If the true state of the world is omega, then I know that the true state is one of the states in pi omega, and exclude the possibility of any state outside of pi omega. Okay. And of course, each agent's partition structure depends on which kind of information is available for each agent. So in this first example, player 1's information includes, he knows the outcome of election, while the second agent only knows the outcome of market. So that's the reason we have different partition structure between agent 1 and agent 2. Okay, so far so good, but we have to have one more extra layer in our theory. So far we have not discussed anything about probability, right? So we only have state space. So in this example here we have 4 states, right? So there are 4 possible state of the world. But so far, we really have not talked anything about probability of each state. But in developing game theory, we really have to discuss about probabilities, because actually at the end of the day, what we have to do is we have to calculate expected payoff for different people in different cases. And in order to calculate expected payoff, of course, you need some probability. Okay? So we have to assign probability of each state to talk about expected payoff and probability of each state, of course. And moreover, we also want to model, our model covers the case that different people have different probabilities about the truth, about each possible state. Okay, so here is what I do, and most game theorists and economists do to model that kind of probabilities. Okay, so we assume that an agent can form some belief about states before observe anything. Okay? So agent there, again, coming back to our example, we have agent 1, agent 2, but we can ask what is agent 1's belief about which state is the true state before he or she observe anything. Okay? So remember that in our story, we are going to assume agent 1 can observe the election outcome, right? But we are asking what is his belief or her belief even before he or she observed the election outcome. Okay? So even before the election outcome is given out, he or she must have some subjective probability for each possible state. Okay? And agent 1 also can, when we talk about prior belief, that kind of belief, we also have to specify what is agent 1's belief about the market outcome as well, right? Agent 1 does not really observe market outcome, but still he can or she can form some belief. Okay? And that belief, we are going to call that prior belief. So we use the term prior to emphasize that that belief is already there even before observing anything. Okay? So it's a prior belief. So in this example, so I'm going to use rho today to stand for prior belief or subjective probability before observing anything, and with subscript that means agent 1's prior belief. So for example, we can this is just example. So we can assume agent 1 has this prior. This is just one possible prior we can think of. And it means that player 1 believes, before observing anything, agent 1 believes that all states are equally likely. Okay? Okay, so rho I means each agent's prior belief. And two comments. First of all, it is not always necessary that different agents have the same prior, right? I mean, different people might have different priors. So that's comment 1. In principle, agent 1 and agent 2 might have different priors. And comment 2, remark 2, in principle again, my prior is not necessarily matching the real probability that each state will be chosen by nature, let's say, or by God. Okay? So for example, let's talk about coin toss. So if you think about coin toss, there are two outcomes, right? T and U, tail and head. I'm sorry, T and head, T and H, right? H and T. But then, if you ask about my prior of coin toss, then my prior will be 1/2 and 1/2. Okay? It's going to be head with probability 1/2 and tail with probability 1/2. But if you think about more carefully, my prior is not really the probability of each outcome. I mean, if you think about coin, actually, it's not really symmetric, right? So if you have infinite mind, like God, then maybe probability of head is 0.49999 and probability of tail is 0.51 something, right? Maybe there is slight difference between head and tail. But anyway, my prior belief is 50-50. Okay? So in principle, I can, or any agent can have prior belief which is different from exact probability of each state. Okay? So in principle, different people have different prior, and also in principle, each person's prior might not coincide with the real probability. Okay? However, just to simplify our discussion, in this lecture, we are gonna assume in most games, we are gonna assume that all agents have common prior. Okay, which means that my prior is same as your prior. It's not necessarily the case all the time, but definitely it's gonna be easier to calculate everything if we assume all players have the common prior. And given that, of course, maybe later when you have to analyze the real world problem, many years later, then maybe you have the case with different prior. But in this lecture, just to simplify everything and convey clear idea to you with clean and simple example, mostly I'm gonna assume the common prior. Okay, so that is just a matter of assumption. And I also often assume that all common prior coincide with the true probability. Okay. Again, in principle, we might have incorrect prior, but we are going to exclude that possibility, at least in this course. It does not mean that the case with incorrect prior is less interesting or less important. I don't really mean that, but just to simplify our discussion. Okay, then with that, we can actually do a little bit more, something more interesting, actually. So, remember that prior belief is belief, subjective probability, I'm gonna assign before I make any observation, right? But of course, once I make observation, I have to update my belief based on my evidence. Okay? So we also have to think about how to update that as well. Okay, so then actually, probably, I think all of you took econometrics last semester, or some kind of statistics course at some point of your life. I don't know which one you took. But then probably it's very likely that you learned at least a little bit about Bayes' rule. And we're gonna use Bayes' rule to update agents' belief after they observe any evidence. So what is Bayes' rule? So basically, this is formula of Bayes' rule. So here, P of A bar B, that means what is probability of A when we know that B is true. Okay? And this is actually the way we calculate that. This is kind of formula, mathematical formula, how to compute P A bar B. Or we read that probability of A conditional on B. Okay? And we're gonna use that Bayes rule. Even if you don't remember anything about Bayes rule, that's okay. I'm gonna explain everything already here today. Okay, so let's think about this case, this story. So now suppose that the nature chooses the true state of the word omega. Okay, so omega will be realized. One state is realized as the true state. Okay, and then each agent can tell, agent knows that omega is one of his or her partition. Okay. I think actually it's better to use our example again. So there are four states, T, D, H, U, and HD. Okay? And agent 1 can tell whether the electron outcome is T or H, which means that his partition structure is like this. Okay? These two states are in the same partition for agent 1, and these two states are in the same partition for agent 1. Okay? And let's say his or her prior is something like this. So this is, he believes that this will be the case with probability 1/2, and this will be the case with probability 1/6, 1/6, and 1/6. Okay? So that is prior belief before agent 1 observe anything. And if you calculate, actually sum of these four fractions is equal to 1. Okay? As it should be. Okay, then let's say player 1, let's say that the true state is this one. Okay? Let's say true state is HU. Hillary wins the election and market goes up. Of course, agent 1 does not observe market outcome directly, but can observe the election outcome. So which means that player 1 only can tell that true state is either HU or HD. Okay? And then after that observation, you have to calculate what is relative likelihood of this state and this state, right? After player 1 observed Hillary wins, now he has to calculate what is probability of market goes up and what is the probability of market goes up. And then, and the only thing player 1, agent 1 can tell is true state is either this one or this one. And then his prior was same for this state and this state, right? And that means if this guy is consistently thinking, inferring everything, then this guy have to assign same probability for this set, this state, and the same probability for this state, even after he or she observed the election. Okay? Let me repeat again. Player 1 can tell true state is either this one and this one after observation of election outcome. But you know what? I actually thought that this state and this state are equally likely. 1/6 and 1/6, 1/6 and 1/6. That means with my observation of election outcome, if I am consistently thinking guy, which he has to or she has to if he is rational guy, then this guy has to say that this probability of this state is 1/2 now, and this probability for this is 1/2. Okay? the true state is HD, then that does not change anything, right? Player 1, agent 1 does not really tell this one and this one apart. So if true state is HD, then again this guy has to believe this is likely with probability 1/2, and this is the case with the probability 1/2. Okay? Then what about true state is here, TU? Then if you compare these two numbers, actually this is 3 times of 1/6. Okay, so if you times 3 to this fraction, then you have 1/2. Which means that after he observed that the outcome of the election is T, Trump wins, then he has to believe this state is 3 times more likely than this state. And putting 0 and 0 for here and here, right? Because he knows that neither of these states is the case. So which means that after observing T, this guy has to believe TU is the case with probability 3/4, and TD with probability 1/4. Okay, so that's exactly what Bayesian updating rule tells us. That's exactly what's going on behind of all this calculation. Okay, so let's check what is this calculation together now. Okay, so P rho I is the probability that agent I has to assign state rho prime when the true state is rho. Okay, so for example here, when true state is TU, we can ask what is belief after observing election outcome, or what is probability of TD. So in that case, omega should be TU and omega prime is TD. Okay? And to put another way, this guy cannot really tell any states in omega, so you can write down this way as well. So rho I omega prime pi omega is what is agent I's probability, subject probability, update probability for state omega prime when this agent knows that the true state is here, pi omega. Okay? Then if omega is not in this set, so in this case, if omega, we are asking probability of this thing, so update probability has to be 0 for this state, and update probability for this state is 0 when true state is TU, because these are outside of the partition. So that is exactly what I mean by 0 here. So for any state which is outside of